Warning: this video is about video. Viewer discretion is advised. I'd like to tell you a story. The year is 2021. I've decided to take video production seriously. I've been running my Patreon for a while and I've gotten a lot more support than expected for articles that mostly talk about how the heck to get anything done in Rust, the programming language, not the game. And so I've got a little bit of money to invest in content creation. And at that point, I've been streaming on and off on Twitch, trying to get famous for playing Spelunky.
11. Interesting.
And occasionally uploading screen captures of my various game dev projects during the Doomdari and so on. So I think I understand how video works. At least a little. I understand that video is made up of a bunch of frames that, if you show them in quick succession, create the illusion of movement because your brain is a big dummy that sees things that aren't there. I understand that resolution is important because even though you can sort of make out that this is a tree, it just looks much nicer if you throw a lot more pixels in. And I understand that frame rate is important too, the number of frames per second. If you have around 24 frames per second, we tend to say it looks cinematic because that's what you get if you go to the pictures. But if you're capturing an SNES game, for example, even 30 frames per second isn't enough because they use tricks, like swapping the visibility of some object every 1/60th of a second so that it appears to your big dumb brain as semi-transparent. And that's about the extent of the understanding I have of video at that point in time, which I imagine matches the understanding of a lot of people who haven't felt the need to suffer the intricacies of what's actually going on underneath. Oh yes, I was once like you, before I gazed into the abyss and then didn't publish anything for 3 months. Sorry about that. So the year is 2021 and I decide, too long have I suffered 1080p. Once the pinnacle of video definition, the full HD miracle that we were all dreaming of, 1080p had become the lowest common denominator. Even the more modest webcams could do 1080p on USB 2.0, no problem. Was the picture quality okay? No, I have yet to test a webcam that isn't just plain awful, but technically I suppose it was full HD, just with weird compression artifacts and stuff, because, well, high-resolution webcams do not send raw, uncompressed frames over to the computer. There's not enough bandwidth for that. Instead, they tend to use MJPEG or H.264, and I don't know if their hardware encoders are just that poor, or if it's just that there's not enough bandwidth to go around, but that tends to look bad. And so I embark on a quest to attain new heights. 4K 60, meaning a resolution of 3840 pixels by 2160 pixels at 60 frames per second. That's just one tiny bunch of problems. The first, I didn't have any 4K screens, which is a problem if the content you're making involves capturing the screen. So I got one and quickly discovered that capturing a 4K screen at 60 FPS requires quite a bit of processing power, more than I had available at the time. In fact, reading up online revealed that this was only the start of my problem, because once you acquire the footage, you want to be able to cut it, do color correction, and apply effects like chroma keying and transitions and all that stuff, and that requires a pretty good graphics card, unless you feel like looking at a bunch of loading bars all day. So I got a present-day graphics card in the middle of the cryptocurrency craze at outrageous prices, which I guess you gotta spend money to make free content. But there was one piece of the puzzle still missing. I didn't own any camera that could deliver 4K 60. I had shelled out for a Logitech Brio 4K, but it could only do 4K 30 or 1080p 60, neither of which were what I was looking for. Because every YouTuber cannot resist making videos about their video setup, I knew most of them used DSLRs, some of which aren't DSLRs, but mirrorless. But what I mean is that they used actual cameras, not webcams. And I had an old Canon lying around, but it too was from decades past and didn't even have clean HDMI output. After installing a custom ROM that did let me have clean HDMI output, it became clear that, image quality aside, it was never going to output 4K, much less at 60 frames per second. So I bought a camera. And because I did my homework, I knew that I would also need an HDMI capture card, so I got one of those too. And finally, I had everything. I started up the Elgato 4K capture utility, cranked up the bitrate, and started speaking unscripted nonsense at the camera alone in my home office, as you do. I then dragged the segment I just recorded into DaVinci Resolve, which immediately showed me a prompt: would you like to set the project frame rate to 59.94 frames per second? I thought I was going proper mad, so I went and checked. My screen captures were at exactly 60 frames per second, but my camera footage wasn't. It wasn't because of NTSC. Stand Up Maths has a wonderful video about this, which I'll link in the description, but essentially, American television was originally broadcast at exactly 30 frames per second, but when color was introduced in 1953, they needed to play with the parameters a bit to make line-by-line phase reversal work. The easiest way was to adjust the frame rate to 2997 so that this fraction gave an integer number. And as you may have noticed, 59.94 is simply 2 times 29.97, which is kind of ridiculous, because values for NTSC were picked to accommodate the frequency of alternative current delivered to North American homes, 60 Hz, but I'm in Europe, so this camera is fed 50 Hz, or I guess it isn't at all, because it's getting DC power through a battery and the charger's input is AC. At any rate, the frequency of my camera's video system has nothing to do with the AC frequency anymore. But the good news is, my editing software takes care of that. I'm not sure exactly what it does, but it works. Actually, I can think of a couple options. It could simply position each frame as if it was a 60 FPS stream, and when it reaches a point where it would be off by a full frame, it could just repeat a frame and it would be aligned again. Because it's not actually 59.94, it's actually 60,000 over 1001. Another thing it could do is interpolate every frame so that it would never offset. Every frame would be a mix of 2 frames because neither frame is exactly at the time we need it to be. But honestly, I feel like repeating a frame every 16 seconds at 60 FPS is probably less noticeable than doing interpolation. Anyway, just like that, I was rid of a misconception I had about video. I thought there was such a thing as 60 FPS, but it turns out there's at least 2. There's true 60 FPS and then NTSC 60 FPS. And not everyone even agrees that NTSC 60 FPS is 60,000 over 1001. Because that wasn't really an issue for my content creation pipeline, I forgot about it for a while. My project frame rate would be set at 59.94 FPS, I would upload that to YouTube, and in the quality picker it would show up as 2160p60. And I never had to think about that ever again. Until the day I thought, you know what, I've already invested all that time and effort into video production, why not go a little further? YouTube works for sure, but I don't really like how they push you to create a certain type of content to drive up the engagement so that you, but more importantly they, can make money off of your videos, you know? And I also felt bad because I've always prided myself in keeping my content ad-free, and it wasn't the case on YouTube. Even before I turned on monetization, it's my understanding that YouTube had been showing ads. Even the folks who support me on Patreon definitely should not have to pay a second time with their attention span. So I thought, and I know these are famous last words, but how hard could it be to just stream directly from my site, providing an alternative place to watch my videos for people who just want to not interact with YouTube at all for some reason? I have the original video in high quality. I have used FFmpeg in the past to transcode some videos so that Twitter upload would accept them because it's very specific about what it's willing to accept, and I don't blame it because it's a mess out there. So here I am thinking, I guess I'm gonna make a video player. And I would like it to be as good as the YouTube player. I would like it to work in Chrome and Firefox and Safari and Edge on Windows and Mac and Linux and Android and iOS. I would like to use modern codecs like AV1 and VP9 that are royalty-free, and I would like to support subtitles with positions and colors in multiple languages if needed. You know, the basics. There's a lot of moving parts to this, and I'm not going to get into all of it. I had to write some sort of CDN so that videos would be cached at the edge. I built a custom React UI on top of an existing MPEG-DASH JavaScript framework. I set up telemetry, got hit by a DDoS attack. You know, the usual. But of all the things to set up, the one that I had to learn the most about was video on demand, or VOD, if you're in a hurry. You may have already downloaded a movie, Nothing copyrighted, of course, but something out of the Blender Foundation, for example, like Big Buck Bunny, which is apparently the only sample video anyone is allowed to use by law. And you would find yourself in a beautiful house with a beautiful wife and a large file. Maybe it's MKV, maybe it's MP4, let's say it's MP4. Have you ever wondered what's in there? Well, I mean, there's gotta be metadata, right? Like what software encoded it, maybe when it was created, stuff like that. And then the rest is just frames, video frames, which are just pictures. Or are they? And audio frames, which are actually groups of audio samples. It's confusing because a sample in MP4 just means a time unit of a track, but in the audio world, a sample is a single point in time value. Like if the audio was sampled at 44.1 kilohertz, there's 44,100 samples per second, per channel. But let's step back. So we have an MP4 file that has metadata and frames, but how are those organized? In the media you're watching right now, there's at least one video track and one audio track, and the player is able to decode and present those simultaneously. So does it go all the metadata and then all the video frames and then all the audio frames? Or does it go metadata and then one video frame, then one audio frame, then one video frame, one audio frame, etc.? Well, it depends what the muxer does, which I guess now we need to learn what muxing is. If we look at the complete pipeline to produce a video with sound, we've got a microphone that's sensitive to sound waves and turns them into an analog audio signal. That signal is then sampled at a regular interval, like 44.1 kilohertz, and with a certain bit depth, like 16, 24, or 32 bits. That's how precisely each sample is measured. Having tens of thousands of samples per second per channel that's a lot of numbers, so it's usually compressed. The raw samples are fed through an encoder for a specific codec like AAC or Vorbis or MP3, which is actually MPEG-2 audio layer 3. And by doing so, we lose some precision, but we save a lot of space. And the result is a bit stream that can be decoded when we need to play it back. Similarly for video, we have some sort of digital imaging device that takes snapshots of how much light of different color hits an array of pixels, and those raw video frames are also fed through an encoder for a different set of codecs, like VP9 or AV1 or H.264, which is actually AVC, which is actually MPEG-4 part 10, or H.265, which is actually HEVC, which is actually MPEG-H part 2. And again, this is lossy compression, but it saves a ton of space and can be decoded by a player such as VLC. Even if you consider these in isolation though, you need more data than just the raw frames to be able to decode those. For audio, you need to know what codec it is, what's the sample rate, how many channels there are, and so on. And for video, you need to know the codec, the resolution, various color settings like color space, color range, and a whole lot of codec-specific data. It would also be nice if you could tell how long a piece of media is without having to decode every frame. In fact, it would be even nicer if you could seek through a piece of media, which would require knowing where in the bitstream are the frames that correspond to a specific time. And that's what a container format does. Once you've got your audio track and your video track, you mux them together into a container like MP4, which is a descendant of the MOV format and the 3GPP and 3GPP2 format, and whose actual Christian name is ISO-BMFF for ISO-based media file format, which is defined in ISO/IEC 14496-12. So the good news is, it's standard. And the bad news is, ça va 198 francs suisses, monsieur.
Auf und auf voll Lustigkeit, rundum voller Freiheit. Nie war mir mein Herz so weit, so voll Seligkeit. Auf und auf, ich war's mit mir von oben klingt. Heit hab ich mein Herz für mir an die Welt verschickt.
Luckily, there's freely available tools to dump the structure of MP4 files, and that's how I learned most of what I know about the format. This XML document was generated with mp4box-std-diso, ran on a Big Buck Bunny sample file. An MP4 file is made up of boxes that can contain other boxes and so on. It's boxes all the way down. The neat thing about this is that all boxes have a 4cc indicating their type and a size. 4cc's are 32-bit integers which can be read as a sequence of 4 ASCII characters. So if a piece of software is reading a file and encounters a box whose 4cc it doesn't recognize, it can simply skip over that box and all of its children because it can read its size. Now the first box we see here is ftip for file type, and it's mostly a list of brands which features are used by the file. Next up is the move box for movie, which contains several other important boxes. An MPEG-DASH box, movie header, which specifies the duration of the movie in the given timescale. If we divide the duration of 10,000 by the timescale of 1,000, we get 10 seconds, and that's the duration of our sampled movie. This sample file contains only one track, so we find a track box, which is filled with other boxes. Among other things, the TKHD box track header specifies the resolution of the video track. Here it's 640 by 360. There's a lot more boxes in there, which we'll come back to later. For now, let's just answer our question, where are the video frames stored? Well, in chunks, and those can be in arbitrary files. Here, the DRAF box, data reference, indicates that the media data is present in the same file. The STSC box, sample to chunk, indicates that the first 146 samples, which in this case are video frames, are in chunk number 1, and the last 154 samples are in chunk number 2. The STCO box, sample to chunk offset, indicates the offset in the file where both chunks can be found, and these happen to point inside of a big MDAT box for media data, which is continuously placed at the very end of the file. Now that's all well and good, but what about timing? You would think the frame rate would be stored somewhere for constant frame rate content. And you would be wrong. Instead, the STTS box, time to sample, describes how long each sample is. Here, it says that each of the 300 samples has a duration of 512. So 512, with a timescale of 1,000, that's half a second? That doesn't sound right. No. Each track has its own timescale. This track has a timescale of 15,360, so a frame lasts 0.033333 seconds. So let's see, 1 over 512 over 15,360 is exactly 30. This is a 30 FPS video, a true 30 FPS video. Now, if someone could remind me why we were learning this in the first place, I think we'll be in pretty good shape. There was something about taking videos seriously, spending a lot of money on AV equipment, and then, making our own YouTube. So up until then, my process was capture my screen, record my face using my camera and HDMI capture card, edit everything together in DaVinci Resolve, add royalty-free music that people can complain about in the comments to drive up engagement, and export it to something like, H.265 in an MP4 container at a high bitrate, and upload it to YouTube, and that's it. But if you want to serve your own video, you need to do what YouTube does, which is pretty involved, actually. First, you need to split each track into its own separate file, actually several files per track. For a single video track, you want to have versions with different resolutions. So we probably want a 1440p version, and a 1080p version, and a 720p version, and that's it. I'm not going any lower. It's not just about the bandwidth, though. Instead of reducing the resolution, I could simply reduce the bitrate, but decoding video is a lot of work. Most devices, even mobile devices today, have a hardware decoder for H.264, but few have a built-in VP9 or AV1 decoder. That's usually done in software. On my phone, for example, the highest resolution that will play back smoothly for AV1 is 1080p at 60 FPS, which happens to be the native resolution of my screen anyway. On top of having to encode at a bunch of different resolutions, you also want to encode in a bunch of different codecs. AV1 is my fave right now, but some devices won't play it, so I also need to support VP9. iPads do support VP9, which is nice, but iPhones don't, so I have to support H.264 as well. For audio, I just go with the single version using the AAC codec, and for subtitles, well, subtitles should probably be their own video. There's too much to say about them. Just picking a set of codecs and resolutions is not enough. You also have to pick encoders and their settings. For H.264, the best encoder out there is hands down X264 from the Videoland team, which makes VLC. For AV1, I picked Intel's SVT AV1 because it's just so darn fast. And for VP9, there's really not that much competition outside of hardware encoders, maybe. LibVPX is pretty much your only choice. Now, these three codecs have different characteristics, so even if you come up with a bitrate target of various resolutions for one codec, it's called constructing a bitrate ladder, it will not apply to other codecs. Question: did I spend an entire week running test encodes and filling out multiple spreadsheets to establish my bitrate ladder? Yes, I did. But how does one even measure image quality? eyeballing it doesn't really cut it. The difference between various bitrate targets can be very subtle and easy to miss. Well, there's several methods. We do have the original video, which, even though it's already a lossy encode of the pictures captured by the camera, is going to serve as our reference. Some metrics are objective. For example, we can calculate the MSE, the mean squared error. It's the sum of the squared absolute differences between pixels of images I and k divided by the total number of pixels in the image. From there, we can compute the PSNR, peak signal to noise ratio. It's 10 times log base 10 of the squared maximum possible pixel value, like 256 if we have 8-bit samples, over the mean squared error. The higher the PSNR is, the more similar both images are. Of course, everyone has their own idea of what an acceptable PSNR value is. The problem with objective metrics is that they don't really look for the same things we do. A relatively high PSNR doesn't necessarily mean that the image will look good to humans, which, despite all appearance to the contrary, is my intended audience. So people have come up with other metrics. VMAF, for Video Multi-Method Assessment Fusion, a collaboration between Netflix and universities across Europe and the US, tries to measure subjective quality. It also takes a lot longer to measure, and that is what I used to come up with my bitrate ladder. Because we now have 10 encodes to do per video, not counting audio, subtitles, and thumbnail extraction, I wrote a tool in Rust that I felt comfortable running overnight. And friends, overnight did it ever run. Even with a ridiculously beefy Ryzen 9, some of my longer videos took over a day and a half to encode. And that's not even the end of it, because after encoding video, you still have to package it. Oh, I'm sorry. Did you think you could just throw these multi-gigabyte MP4 files at a browser and it would just play them seamlessly? Well, you're correct, it would, but that's not what we want. What we want is ABR, adaptive bitrate, which means the player should be able to switch seamlessly from one quality to another as the network conditions change or the size of the viewport and so on. And for that to work, you can use a tool like Shaka Packager that generates files that follows the MPEG-DASH specification. So the packaging process takes all the different variants of our video track, different codecs, different resolutions, and it remixes those, either splitting them in segments or keeping them as one big file, but making sure that it knows the exact byte range of the initialization segment, which has all the information needed to decode compressed frames, and the index segment, which has timing information for a segment. It also generates an XML manifest with the MPD file extension that lists all the tracks and their variants with the codec and resolution and bitrate and the byte ranges of the initialization segment and the index segment. And then once that's done, you can upload those files somewhere like cloud storage, I don't care. And then in the browser, something like Shaka Player, which leverages the media source extensions, is able to queue up segments of whichever quality it thinks is best at the moment and switch anytime it wants to another quality at the segment boundary, which is the reason you want to keep segments relatively short. I have mine at around 4 seconds, I think. So now, I know what you're thinking. Why am I watching this? Who is this for? Does he really think people are just going to watch this and then go make their own YouTube? And if not, why is he making the video? What does it say about him that he feels the need to explain all those details? Is he just bragging? Does he have a compulsive need to just go on and on about any technical topic whatsoever, regardless of how useful it is to those who watch it? What does it say about me that I'm still watching this video, even though he's now engaged in a bit that clearly should have ended a minute ago? What do I have to gain in learning any of this, which I'm probably never going to have the chance to apply in real life? What do I have to gain in anything? Is anything worth learning? Does something have to be useful to deserve to exist? Am I useful? Am I art? And the answer is, yeah, I know. But you do have a point. I think we should look at more examples of what this looks like in real life, because it's been a little bit theoretical so far. So let's take this Big Buck Bunny video, which we've already looked at with MP4 Box, and run it through Shaka Packager, asking it to remix it and generate an MPD manifest. And first of all, this is what the manifest looks like. So from the get-go, you can see that this has big design by committee energy. It's supposed to support anything under the sun, but in practice you want to keep to a very small subset. You can have multiple periods, but you often just need the one. Adaptation sets are kind of like tracks. Video tracks are typically grouped by codec and audio tracks by language. Each set can have multiple representations, which should be the same content, same codec, same language, but can be different resolutions and bit rates, and that's what the player can switch between depending on things like the viewport size, the current network bandwidth, etc. Here it refers to that MP4 file it remuxed, and we have the byte ranges for the index and the init segment. Speaking of that MP4 file, let's take a look at it. It starts with a file type box with a few extra brands like dash. Everything in the movie and track header boxes looks the same. The segment index box is new, that's what the MPD manifest was referring to. It announces 2 segments, and here's the first one. First, a movie fragment box with a track run box that has 1 entry per video frame. It seems like a combined version of the time to sample box and the sample size box, which, even though they're still present in the file, are empty. Media data box follows, containing the actual video frames, and then, as announced, a second movie fragment box, followed closely by its own media data box. This is interesting from an optimization standpoint. If I told the packager to generate multiple files, I could start uploading them while it's still processing the next fragments, and that might speed things up a bit. Now, before we get into it, let's check that the generated file does work. We can serve the folder with a static file HTTP server like SFZ, load it up in the -if reference player, and it works. Yay. Now, I'm intrigued by the multi-file approach though, so let's try that too. We just need to tune the command line a little bit. The generated manifest looks a little bit different. Now we have a segment template element with a segment timeline. This replaces the segment index that was previously in the single MP4 file. The main output file is now just the init segment. Again, we have the file type box, then all the movie and track metadata, but there's no actual media data in there. And here's what a fragment looks like. Instead of file types, it has segment type, an index with a single segment, and then no movie box, no track boxes. We go directly to the movie fragment box with the track runs, and later the media data. Now this makes sense if you consider what the player has to do when switching to another quality. It needs the init segment for that representation, and then the segment at the current timecode. It's a bit more convenient to have them split like that instead of having to do range requests. Let's just check that this one plays 2, and it does. The sample here is pretty short, but we can see in the Chrome DevTools that it first requests the init segment and then each segment in order as they're being queued. So I could definitely use fragmented MP4 to speed up the process of preparing my videos for streaming on my website. As Shaka Packager writes these files, I could upload those to S3. The thing is, that's not the bottleneck at all. Arguably, the longest part is researching and then writing a script and then shooting and then throwing away all the footage because I hate it, and then rewriting the script and then shooting again and then having a special thought for the people who think they can hear my mouth noises too much, and then going to the store to buy apple juice and sugar-free gum and editing and synchronizing subtitles. And the problem is I can't make the production part any faster without making the video any worse. The actual part that I want to optimize is the encoding. That's what takes the longest, that I'm not directly involved with. That's what keeps the video from going live as soon as I'm done with it. So even if at the very end packaging produces many small files, I still have to encode from one large reference file to 10 different variants that have different codecs and resolutions. And even if I do these in parallel, I'm still limited by how long the longest encode takes. But the thing ends up being fragments anyway. If I could fragment the reference file and then encode all those fragments in parallel on other people's machines, cloud machines, and then still somehow generate something that is MPEG-DASH compliant so that it will play in browsers and iPhones and stuff, that would save so much time. And it's especially attractive because the workload I have requires a lot of processing power over a very short period of time. It would not make sense for me to buy a dozen Ryzen desktop computers. I wouldn't know what to do with them when I'm not encoding a video, plus the electricity bill would go through the roof. But Amos, didn't other people already solve that problem? Couldn't you just pay them to encode your... Yes, of course, but they take like 1,000,000% markup on the cost of computing, and the whole point of doing this is kind of a challenge, right? Compute is now a commodity, and there's a bunch of open source software around, and is it even possible? Is it feasible for a single person to set everything up from start to finish exactly the way they want it? That's what I was going for. So no, I'm not just going to pay someone to encode my videos, otherwise what am I going to make videos about? Anyway, the new plan is to fragment the videos ourselves before encoding, and that is a lot more involved than I thought it was going to be. Because remember when I said video frames are just pictures? That was a lie. Just like constant frame rate is a lie. I have this 29.98 FPS video here, and all the frames are exactly 20 units of time except that one, which is 21. So you know, I guess time is not an exact science. That's not even really the issue here. Remember when I talked about webcams that use the MJPEG to send frames compressed to the computer because there's not a lot of USB bandwidth? Well, MJPEG is just, you take a frame and you compress it as JPEG and then ta-da, there's no link between two frames. It's not using temporal information to make the video stream smaller. It could be sending the exact same frame twice because you left your webcam and went to buy freaking apple juice. It would still re-encode each one of them separately, which is not the case for other video codecs like H.264. Those have to start with what we call a keyframe or an iframe, but then you can slap some p frames, p for predictive, that uses the previous frame's information and says, oh, that arm there, it just kind of moved up a little bit, like this whole area, there's some motion vectors that say, oh, this used to be here, but now it's there, and so I don't need to tell you the color of the arm or the shape or whatnot, because you just move it up a little bit, and then of course, it's not just like that. If you move the arm up like that, it's still going to be wrong because the arm is 3D. So here's the difference between what you got when you moved the arm up here and what's actually in the new picture. But that's still less information than telling you all about the background that never changed. And that explains why some frames are much larger than others. You can see in this 4K video here from an iPhone, the first frame is over a megabyte, but then the other ones are like 400K, 200K, 100K. It's wonderful. And it goes deeper still. There's B frames, B for bidirectional. They use information from both the previous frame and the next frame, and those can get smaller still. And the Big Bug Bunny video that we actually does use those. The first frame is 76 kilobytes, and then the next one is 184 bytes. That's nothing. And so these are a way to make the same video quality fit in a lower bitrate, as long as you give the computer time to think about it. Because to make B frames, it has to know about a bunch of different frames and decide okay, I'm gonna make a series of 4 B frames, and then I'm gonna make a P frame, and then, because at some point we're gonna have to use an iframe again, and actually that is a good point. Why would you ever want an iframe again? Wouldn't you want just B frames, the best frames? Well, first of all, no. That's it, that's the answer. Yeah, but think about it. Imagine a scene where I'm talking to myself in my home office, and in the next scene, I'm running through a field of flowers. When we cut from one scene to the next, there's 2 frames that have almost nothing in common. Lighting is completely different, all the colors are different, there's none of the same shapes. You would not save anything by using a P frame or a B frame there. But there's another reason when you consider video on demand with adaptive bitrate switching. Every fragment has to start with an iframe. Because if you switch from one resolution to the other and the first frame you get is a P frame, you're missing the information required to construct that frame from the previous frame, because you don't have the previous frame, you have a different one. Apparently AV1 has the concept of S frames, which let you switch, I guess the S is for switch, between different resolutions.
If I might tell you what an S frame is, it's a switching frame. It's a P or inter frame that only uses the reference frame. All the other information must be provided within the elementary stream.
If you try to reconstruct a P frame from the wrong previous frame, you get some weird looking stuff, which is very fun as a creative outlet and nightmare fuel, but not what you're looking for if you're running a streaming service. But remember, we want all fragments to have about the same duration, so that rate switching can occur pretty much anytime it wants to. And also that way you don't have to list the duration of every fragment, because it's going to be different. You can just say my fragments are this long and there's 1,000 of them. So I guess, okay, let's just force the encoder to, when you're exporting from DaVinci Resolve or something, to emit iframes every so often at a regular interval. That's gonna be enough, right? Wrong. Because remember how I never said, but we just kind of assumed that frames would come in order? Like if you're looking at the symbol list for a video track and you're going and decoding frames one by one, that's also the order in which the frames should be shown on the screen? Well, that's not true. You thought timestamps were messed up, because they want to store integers, right? So now you have to use a timescale, because it's not an integer number of seconds. And the timescale of a container is not the timescale of each individual track. And inside of a framework like FMPEG, it's not a timescale, it's a time base, which is 1 over the timescale. So now suddenly you have to deal with fractional numbers. And no, you cannot just use floating point numbers, because then everything's going to be wrong. But then it turns out that the timestamps for packets, which is a container's idea of what a frame is actually not a PTS, it's not a presentation timestamp, it's a DTS, a decoding timestamp. And it turns out that if you give the computer enough time to think, to really squish the video into a tiny file, not only will it come up with P frames and B frames in your presets, but it'll also reorder frames, because it's just more convenient. It uses up less data to encode the difference, we just put them in that order. So it's not enough to just emit iframes at the fragment boundary because it could still be out of order. So that means the decoder needs to buffer frames. It used to think buffering was just a networking thing, like, oh, who knows if you're still gonna have the internet 5 seconds from now, so let's just gather up a bunch of data. But no, it turns out the frames are freaking out of order. So you need to buffer those so the decoder can decode them out of order, and then the player can reorder them and composite them at the right time. And that information is all in the MP4 itself. We kind of glossed over it the first time we looked at it, but if we go back to our very first MP4 XML structure file, there's a composition offset box. And so for each sample, it says, so you're decoding it now, but you're going to present it like this amount of units of time later. In this video, all samples have a duration of 512. The first sample has a composition offset of 1024, which means that even though its DTS is 0, its PTS is 1024. It should be presented 2 frames later. The second composition offset is 3584, which means it should be presented 7 frames after it's decoded with a PTS of 4086. It's all very confusing to do by hand because the composition offset is relative to the DTS, so I put it all in a spreadsheet for you to look at. The picture numbers here are 0 based, so it should start with 0 and then 1, and here we go 3, 4, 5, 6, 7, 8, 9, 10, all extremely out of order. And I hear you asking, yes, you in the back, where are the first 2 frames? There's no frame 0 and there's no frame 1, so where did they go? Well, nowhere. Frame number 2 is the first frame we can present. So what do we do for the first 0.06 seconds of the presentation? Do we just show a blank screen? Do we have a colorful man in a top hat playing piano? No, we can't have that. It's not the 1920s anymore. That's why we have an edit list. The edit list box appears, says the media duration is 10,000 and the media time is 1024, which is hilariously confusing because the duration is in the movie's timescales. That actually means 10 seconds, and the media time is in the track's timescale, so that actually means 2 frames, which works out because we started frame number 2. So what that means is offset all the presentation timestamps by 1024 to the left, and everything will be fine. But Amos, what do you want? Are you gonna ask me if they couldn't have simply put negative composition offsets instead? Maybe so, I don't know. But that number there is an unsigned 32-bit integer, and so the best thing we can do is move the whole timeline to the left and pretend none of this ever happened. Which brings us to fragmenting files before encoding. I said emitting iframes wasn't enough. We needed each fragment to be self-contained, which means that no matter what order the frames are in, they cannot refer to frames outside the fragment by virtue of being P frames or B frames. But they also cannot have presentation times outside the fragment. It's like we need a self-contained group of pictures. And that's exactly what it's called, a group of pictures, or GOP. So when you go on Stack Overflow complaining about fragment and MP4 and some ass replies, oh, you just set the GOP size to 230. That's what it freaking means. But it's not over. No. FFmpeg is a wonderful tool, and it comes with a wealth of little tiny bits and pieces that you can combine to your heart's content. It has a segment muxer, so you can give it some MP4 file and give it a segment duration in milliseconds, and it'll output individual MP4 files. In fact, let's try it. We'll give it the Big Buck Bunny video and ask for 500 milliseconds segments. We should have 20 segments, and we get 2, because you can't do miracles. There's only 2 keyframes on the input video. There's one at the very beginning, and then one around 8.3 seconds. Which explains why, if we look at the duration of the segment with ffprobe, we have 8.4, and it starts at 0.066 seconds. Why would it start at 0.066 seconds? I don't know. Does it have something to do with the fact the first unadjusted PTS is 1024, which is 2 times 0.033 seconds, and that's what you would get if you ignore the edit list? Anyway, at any rate, it also has a concat muxer. So if we just take the .ffcat list that generated and reassemble it, we can see that our start time is 0 again, except the duration is now 10.07 for some reason. And if we dig deeper, we can see the original file has 300 frames, but the reassembled one has 302. Where did the 2 frames come from? How did it invent 2 entire new frames? Everything seems fine until the 8.3 seconds mark, where the reassembled video was suddenly off by at least 1 frame. Now, I've extracted all 302 frames and went through them manually, and it turns out that frames 250 and 251 are actually the same, which doesn't tell me where it got the other frame. Anyway, what this means is that I can't rely on FFmpeg built-in segment muxer, which I knew already because it resets timestamp to 0 when starting a new segment by default, and that's not what you want when making MPEG-DASH fragments at all. Sure, you can disable it, but at that point, I just don't trust it with timestamps. And by the way, I can't use the dash muxer either, because yes, FMPEG does have a muxer that generates an MPD manifest, so check package was never needed in the first place, and all the fragments and everything. But it's meant to have all the inputs as a single file, whereas in my case it's already fragmented. Calling it separately again makes the timestamps all wrong. Also, the dash muxer is meant to work one of two ways. Neither of these work for me because I'm passing custom I/O contexts, which actually perform asynchronous I/O in Rust via Tokyo. And FMPEG's I/O context is a leaky abstraction. The dash muxer actually parses the given pseudo URL, and if it's a FI protocol, it issues rename syscalls, which is a big no-no when you expose a virtual context. Sure enough, I went through the FMPEG source and read the dash muxer, and it turns out you can just use the MP4 yourself if you're willing to init some MP4 boxes yourself. Luckily, it's a pretty simple box. The next problem is generating the MP file without the help of FMPEG. It's almost trivial, except for the part where you need to generate accurate codec strings, something like VP09.00. Those weird numbers are codec specific settings, and in this case, they're not part of the MP4 metadata. You actually have to parse null units in the case of issue. But I'm pretty sure browsers don't actually read all those numbers anyway. I'm not sure why they put it in the MPD manifest in the first place. It seems like all the information they need to record the bit stream is already in the initialization tick. But you know me, if you tell me there's a right way to do this, I'm gonna try. I haven't really got started on the splitting code yet because frankly it's hard to since at this point, who could blame me? You think you're gonna make a video platform, it's gonna be all glamour and stuff, but as it turns out, you end up doing a lot of CRUD stuff and job queues and whatnot. If someone had told me going into it that it would be that much work, I've not done it at all. Who am I kidding? Video is too magic for me to know. And you don't really like to do deep stuff, but also wide. Well, anyway, thanks for watching, and don't forget to support me on Patreon if you like the content. Hey, wherever you go, come back!